Hello everyone, in this video we're going to be picking up where we left off in section 10.2, which is plane curves and parametric equations. So example 4 here. Sketch the curve represented by x equals cosine of theta and y equals 4 sine theta for theta that varies between 0 and 2 pi by eliminating the parameter and finding the corresponding rectangular equation. Okay, so in this case our parameter is no longer t, it's theta. But again, t theta, it doesn't matter, that's just a variable, right? And so normally what we would do is typically we solve one of the equations for our parameter and then plug it into the other equation, right? That's kind of the method we looked at in the last two examples. However, in this case, that's not going to be very helpful because if I took like x equals 3 cosine of theta and I solve for theta, I'd get x over 3 equals cosine theta, and then I try to get cosine inverse of x over 3 equals theta, and then things get a little bit more complicated. So that's not really the route we want to go on. The route that we want to go on is to remember the following identity, that sine squared theta plus cosine squared theta is equal to 1. Remember that Pythagorean identity. So that's what we're going to use here. So I look at the first equation, I say x equals 3 cosine of theta. So what does that mean? That means that x over 3 is equal to cosine of theta. I see that y is equal to 4 sine theta. So that means that y over 4 is equal to sine theta. So now I know what sine and cosine are. So I can use my identity, my Pythagorean identity, that sine squared theta, or actually even I could write it as cosine squared theta because that's just going to make it look better for our equation. You'll see why. So cosine squared theta plus sine squared theta. I'm just changing the order because addition is commutative. So I end up getting cosine squared theta plus sine squared theta equals 1. So what is cosine? Cosine is x over 3 squared plus sine squared. So that's y over 4 squared is equal to 1. So I end up getting x squared over 9 plus y squared over 16 equals to 1. So now this is starting to answer the question of why did we start chapter 10 with those conic sections? Well, because some of these parametric equations that we're going to look at are conic sections. And this is an example, right? This is not a sphere because with a sphere we'd have to have the same rate, we have to have the same denominator under x and y so we get a radius. So this is actually an ellipse, right? And so let's talk about some properties of this ellipse. First, we know that since the y variable has the bigger denominator, this is a vertical ellipse. It has a vertical, like transverse axis, whatever. I can't remember the exact phrasing, but it's a vertical ellipse, right? So in other words, it looks like that. Okay. Now, because of that, in order to get our vertices, well, actually, we can just write what our vertex is. So my vertex, or not my vertex, sorry, my center, that's the other thing we want. My center is the first set of information I get. So my center, remember we label it by h and k, that is just what I'm subtracting from x and what I'm subtracting from y. In this case, I'm not subtracting anything, so my center is 0, 0, right? And now the other important information that we need in order to sketch this is to find the vertices, right? So right now I know where it's centered at. Now I want to figure out these values up high and up low, down low, right? So how do I find those? Well, let's move this down a little bit. Let's figure out what all my values are, like we did it before. So my h and k I've already talked about. H equals to 0, k equals to 0. Now a, remember a is always the bigger one, so a is equal to whatever squared makes the bigger one. So in this case 4, because 4 squared makes 16, and then b is whatever squared makes the smaller one, which is 3. Right? So remember, in order to get my vertices, what do? I add and subtract a to my center, since it's a vertical one. right? So in order to get my vertices, what am I going to do? The x value stays the same, but I'm going to take my y value of my center and I'm going to add or subtract, whoops, need blue here, add or subtract that biggest value, which is 4, or b. Right, so in this case, my vertices are 0 and 4, and 0 and -4, right? And then in order to get my how far wide I go, remember that this, if I were going to draw this width right here is 2b, right? So I should draw that in red. This width of this is 2b. So if I take the center, and I know that, so if I take my center, which is 0, 0, and I subtract b from both sides, so I get h plus or minus b, then that's going to give me those values that those other kind of, not the vertices, but the other points that are on the graph that are exactly like a right angle from my vertices, right? So h plus or minus b is going to give me those values, which will help me draw it, right? So this is going to be -3, 0, and 0, -3. So now we have all of our information to sketch this graph, right? Again, this is why we looked at conic sections. So now I get 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. So if I were going to sketch this, I know that this point 4, 0 is on there, -4, 0, 3, 0, and -3, 0 are all on there. So it looks like this. And of course, mine you can't really tell which is bigger and smaller because I didn't make my axis perfect, but you get the idea. The other thing we can do, remember I guess I didn't really talk about this yet, but the whole point of why we would ever want to switch from parametric equations to the x and y coordinate system is just to help us graph, right? It's always better to have the parametric equations because they give us more information, right? So let's kind of think back to the parametric equations and let's make a t, x, and y chart, right? So that way we can have some more information about where the graph is, right? We know it's this ellipse, but let's have some information about at what times or what angles my graph or what theta values are. So let's look at theta equals 0. Let's look at pi over 2. Let's look at pi, 3 pi over 2, and 2 pi, right? Because those are like kind of the whole number values for our guy. So if I did this, I would get cosine at 0 is 1, so I'd get 3. Sine at 0 is 0, so I'd get 0. Cosine at pi of 2 is 0. Sine at pi over 2 is 1, so I get 4. Then cosine at pi is -1, so I get -3. Sine at pi is 0. Cosine at 3 pi over 2 is 0. Sine at 3 pi over 2 is -1, so I get -4. And then cosine at 2 pi is 1, so I get 3. And sine is going to be 0, right? So what does that mean? That means right here at 3, 0, that's when theta equals to 0. And then I go up to 0, 4. So that's this guy. This is when theta equals pi over 2. So my orientation, my graph looks like this, right? And then here, this is theta equals to pi. Keep going around the curve. Theta equals to 3 pi over 2. Keep going around the curve. Theta equals to 2 pi, which is the same as 0. Right? So again, I gain more information from the parameters. I just use the x and y coordinate system to aid in my drawing. Right? So the same way for these two equations here. As always, eliminating the parameter is really just a helpful way for us to sketch the graph. Okay, so now one other thing that we should learn how to do is if we have the x and y coordinate system, how are we going to find the parameters, right? The parametric equations, right? So we looked at, hey, if I have this, if I have these two parameters, I can rewrite it as an x and y equation. Now, if I have an x and y equation, how am I going to write this as a set of parametric equations? And it's actually pretty easy. So I want to look at this example here. Find a set of parametric equations that represents the graph of y equals 1 minus x squared using each of the following parameters. So t equals x. So that's what I'm setting it to, t equals x. So notice that's just what x is equal to, right? So then what do? Well, I know t equals x, so I can go into the other equation, the rectangular equation, 1 minus x squared. And now instead of t equals x, right, I can write this maybe a different color. If I write this as t equals x, that means I can go into this equation, 1 minus, and now instead of writing x, I can write t. So I get 1 minus t squared. So my set of parametric equations is x equals t, because that's what we set it equal to, and then y equals 1 minus t squared. So that's my set of parametric equations. And often that's what we're going to be doing to find parametric equations. We set x to be anything we want it to be in terms of a parameter, and then we plug it into the equation to get whatever y should be in terms of t, right? Okay, well, say we wanted the slope at the point t to be our parameter. So what we're going to do in this case is I'm going to say, okay, I want m is equal to dy over dx, right? So dy over dx, that's the derivative of our equation, right? So the derivative of our equation is minus 2x, right? The derivative. So m is my parameter in this case. My parameter is no longer t because I'm calling it something different, right? Which is fair game. So m equals minus 2x is my equation that I get from that. So I can solve for x in order to get my x equation, right? Divide by negative 2, divide by negative 2. I get m over negative 2 is equal to x. That's my x equation, right? Now, I can plug that into my y equation to get my y, right? Y equals 1 minus x squared. But we know what x is, right? I guess I don't need y equals 1 minus negative m over 2 squared. So 1 minus negative m over 2, the negative squared makes it positive, so I get m squared over 4, right? So y equals 1 minus m squared over 4 is another parametric equation that represents another set of parametric equations that represents that curve, right? And again, the only difference between drawing it with these parametric equations or these parametric equations would be just maybe the speed of it, right? So I guess maybe I should write y equals negative m over 2. Y equals 1 minus m squared over 4, just so it matches. Okay, so now let's do one example. Find two different sets of parametric equations for the rectangular equation y equals 6x minus 5. So always the easiest one is just to say, let's let x equals to t, right? That's always a really easy way to do this. And then what does that mean for y? Y equals to 6x minus 5. Well, what is x? X is t, so 6t minus 5. So I get the set of parametric equations. X equals to t and y equals to 6t minus 5. Right? That's always an easy one to do. So now we need to find another set of parametric equations. So again, we really can make it, x can be any function of t, and then y will just be dependent on whatever I make x. So let's say, for example, I made x equal t plus 1, right? That's fair game. If I do that, then y equals 6x minus 5, so y equals 6 times t plus 1 minus 5, so 6t plus 6 minus 5, so I get 6t plus 1. So that's another set of parametric equations. X equals t plus 1 and y equals 6t plus 1. And I could literally do anything I want. So x equals the square root of t. If I did that, then y equals 6x minus 5, so y would equal to 6 radical t minus 5. So that's another set. X equals radical t, and y equals 6 radical t minus 5. And if I sketched all these, I would still end up getting the same curve. Again, one might go a little bit faster through the curve than another one, but that would be the only difference. Right? All right, that's all I have for this section. Thank you.